Well, today we're going to talk about the derivative, and we've already talked in past classes about determining slopes of secant and tangent lines to a given point. What the derivative is finding the slope of the tangent line at any point on the function, where x is defined, that is. And what this will produce is a formula that allows us to calculate the slope at any point we choose to find. So the derivative is a formula for finding the slope of the tangent line at any point. Alright, so let's just break down what all that means and how that's going to work. We're going to start with a function, and we've got a point on the function that we will want our line to be tangent to. So our point of tangency is x f of x, and the end result will be that we will want the slope of the tangent line at the given point. Now keep in mind that x is movable, so that point could be anywhere, thus the tangent line could be anywhere, thus the slope we get will be changeable, and therefore what this process is going to produce is a formula that allows us to find the slope at any point. Alright, now we know again from past classes that to find the slope at one point we have to begin with taking a slope at 2 points, a secant line. So let's take a point close by, and I'm going to label this point a couple of ways I can label it. First of all, I can say that the horizontal distance between these 2 points is h, making this coordinate x plus h. So there are the coordinates of that point. Alternatively, I could call this point just some other variable. Let's call it w. And I could label this point alternatively w comma f of w. And our secant line joins those 2 points. Now we know that the slope of the tangent is equal to the limit of the slope of the secant. So our secant slope in red, taking the limit of that, will produce the slope of the tangent. Alright, now let's set this up, and we're going to set this up in 2 ways as I indicated, because we've got our second point labeled in 2 different ways. So first of all, using these 2 points to set up our slope, the idea here is that we will do y2 minus y1 over x plus h minus x, which is h. In other words, h is the run. And to turn that secant slope into a tangent slope, we need to take the limit as h approaches 0. And that gives us the slope of the tangent line at x f of x, which we denote as f prime of x. The slope of the tangent line at the point x comma f of x denoted by f prime of x. And there is one formula, the most common formula for the derivative. If I choose to use this point with this point to calculate the slope, so I'm just going to come up with an alternative way to get the derivative. I will take f of w minus f of x, subtraction of the 2 y's over subtraction of the 2 x's, w minus x, and in this case we are wanting to make w approach x. And there's an alternative formula for the derivative. Alright, now the first formula is more commonly used than the second, but you need to come to recognize both as representing the slope of the tangent line at any point. Alright, and just as indicated, we have a couple of different notations, symbols for the derivative. One is as used above, f prime of x. Another one is dy dx. It's the change in y with respect to x. Or sometimes you'll see y prime used. You'll get used to these different notations as we move along. Alright, let's use the definition of the derivative that we've just discussed to find the derivative of a specific function, 1 over x, which we know looks something like that. And so what we want are the slopes, is the slope of the tangent line at any point, which is the derivative, f prime of x. And as we set it up, limit h approaches 0 of f of x plus h minus f of x all over h. Alright, so I now need to apply the specific function to this. F of x plus h will be 1 over x plus h minus f of x, 1 over x all over h. This formula is going to simplify to a formula that will allow us to find the slope of the tangent line at any point. So we need to simplify. Alright, so we have fractions within fractions. I'm going to multiply numerator and denominator by the common denominator of the numerator, x times x plus h. So the derivative is the limit as h approaches 0, distributing through. I would get x minus x plus h all over x times h times x plus h. I'm not going to multiply out on the bottom because I know to cancel I need things in factored form. I need to manipulate the top to simplify it. And I can see if I do that, minus x minus h, the x's will cancel out and I'll have negative h. And now I'm ready to cancel. My h cancels out. And I'm ready to do the derivative. As h approaches 0, the bracket will become x, and so my derivative will be negative 1 over x squared. Alright. Now, what exactly does that mean? Well, the question asks us to use our result, use the derivative to find the slope of the tangent line at x equals 2. So at x equals 2, I can visualize that my tangent is similar to, somewhat like that. It's got a negative slope, the line is falling, which means a negative instantaneous rate of change. So to find the slope of the tangent at that specific point, all I need to do, slope of the tan at x equals 2, is I simply place 2 into the formula for the derivative. The derivative is the slope producing formula at any point. In this case, I want to know the slope of the tangent at x equals 2. So it's 1 over 2 squared, and the slope is negative 1/4, meaning that the graph at that point in time is dropping 1 unit of y for every 4 units of increase in x.